So let's go in deeper into this topic. All right, potential energy. These are stretched rubber band. This is elastic potential energy. This is chemical potential energy. What does the apple have? Well, the apple is like a stored chemical potential energy, right? Because it takes energy from the sun. All right, the leaves of the plant take energy from the sun and undergo, well, this is called photosynthesis. All right, the light energy from the sun is converted to chemical energy in the sugars of the plant. This is then converted, all right, and as you know, when you eat the apple, well, a good, nice, juicy apple is always sweet. And why is it sweet? And what are the fibers made of? Well, they are made of cells, okay, and they're made of sugars. And this basically is what we call the stored chemical energy, right? The chemical potential energy of the apple. What is kinetic energy? Well, kinetic energy is energy that a body has due to its motion. Now, pay attention. To have kinetic energy, the body or the mass must move. If it is not moving, you cannot say that it has any kinetic energy. As you can see in this formula here, we can actually calculate the actual amount of joules of kinetic energy by using this formula, this simple formula, half multiplied by the mass of the object in kilograms multiplied by the speed of the object squared. Alright, so this is how you calculate kinetic energy using a formula. Alright. Non-mechanical energy. Mechanical energy, as you can see here, okay, is made up of potential energy and kinetic energy. Alright. Examples of non-mechanical energy is heat, sound, light, and nuclear. Alright. Why do they call it non-mechanical energy? Well, you can guess that the word mechanical can be derived from machines. Okay, the use of machines to help mankind do work or make work easier. All right. So let's have a look at something interesting. Conversion of energy. How is energy converted from one form to another? All right. To illustrate this best, well, let's go back to our video and check it out before I go back into this topic on conversion.
Now, what would happen if suddenly there were no energy in the world? Well, first of all, there'd be no electricity, so that wouldn't they? And then the wind wouldn't blow anymore, so the clouds would stop moving and the flag would stop blowing. There would be no more movement. The cars wouldn't move. As a matter of fact, all the lights would go out. Cold, dark, dead world. But lucky for us, we don't have to worry about that, because energy is everywhere. Energy is everywhere.
Hey friends, are you like a lump on the plastic-covered couch, all potential energy? Do you dream of someday taking charge and fulfilling the kinetic energy?
Check this out. It's an energy demonstration. As I wind up this propeller, the rubber band stores energy, and that energy can be released to make the airplane fly.
But what goes behind the physics, okay, or the science of the roller coaster? Okay, here I have a very interesting simulator. Okay, as you can see, this is the design of the ramps, the heights of the 3 hills. Alright, this is a 360 turn. Okay, so over here you can find the different heights. So if I move this dial up, we can see the height going higher. Okay, and later you will be able to see the speed of the car. Okay, the faster it is, of course the car will move faster. And you can even vary the mass of the car. The bigger the mass, you can increase it or you can reduce it. Interesting, huh? Gravity also can be simulated. Okay, if you increase the gravitational pull of the earth, alright, just move the slider. And friction too, because as you know, there will always be friction, right? When a car moves down, there will always be friction. You can reduce it or you can increase it. Okay, let's have a simple demonstration. Let's reset everything to its original setup. And let's begin the simulation. Look here as the cart moves down the ramp, up the second slope, and tries to go around a 360 loop. Unfortunately, as you can see, it fails to do so. Okay, there's a very nice oscillating movement here, back and forth. But more importantly, this design of a roller coaster fails. Okay, so let's see what we can do. Well, let's try to perhaps increase the mass. Since, alright, increasing the mass will increase both the gravitational potential energy at the start, okay, because it will fall down harder, right? And as you learned earlier on, kinetic energy is related to half mass times velocity, or the speed squared. So it will also move down faster. So let's see what happens. When you increase the mass, it moves faster, up, down. Does it go over? Hey, unfortunately, it doesn't also. Okay, in fact, if you look carefully, it almost hit the same spot as the original one when the mass was back to its original. So let's see what other things we can do. Let's reset this again. Okay, let's try reducing, perhaps reducing or increasing the height of the first hill. Okay, if we move the height of the first hill, let's try. Maybe higher is better. When the first hill is higher, there is greater gravitational potential energy at the start. So when the roller coaster falls, okay, it is now converting its gravitational potential energy into kinetic energy, and therefore it should move faster, and well, it should go over, right, the 360 loop. And let's see what happens if we do that. It comes down, goes up, and whoa, it flies out of the track. So as you can see, something is challenging, don't you think? The roller coaster needs to travel fast enough to overcome this, but it cannot be so fast that it leaves the track. As you saw just now, it was like a projectile motion going up and jumping off. Oh my goodness, if it happened, I think nobody would survive. So what do we do now? What can we do? Okay, engineers therefore have to maybe design or calculate using physics or science, alright, and understanding gravitational potential energy and how it works, one can conclude that perhaps if this energy at the start is going to be the energy that the roller coaster has, so what you can conclude is this loop here should be lower than this loop. Okay, that is of course if there is very little friction, because friction can actually convert the energy into wasted energy, waste energy, WASTED, wasted energy, in the form of heat and sound. Okay, this energy is wasted, so whatever energy is stored at the beginning, okay, may not be enough, alright, when it tries to go over this loop. Okay, so the important point is this, that this loop here must not be higher than the very first loop. So let's see what happens when we simulate this. Alright, now depending on how we angled it correctly, as you can see, oh, it went up and came back down. Unfortunately, it wasn't enough. Alright, so there must have been some friction playing a part. Now let's take a look at the dial and shift it until we reduce all the friction and see what happens when you simulate this. Okay, without any friction, you can see, yo, it works.